Okay, let me return to this example. So here we calculated all the metrics we've just discussed for the polynomial fit, and there is a nice observation here. As we can see, train error, say train error 2, is much better than the test error. And actually, these two types of errors can be seen as two ways to describe the performance of your model. So the first one is the way to describe the complexity. Okay, in the training data fit, it's one measure of complexity of your model. If you have a simple model, say a constant one, then you have too low train errors, say too low train error square, and too high MSE and other metrics. In contrast, if you have a very complex, a very flexible model, then you can just interpolate all the data and your train errors will be 0 and train score, error2 score, will be equal to 1. So it's more or less simple part. But what is really interesting for us is how can we use our model, train model, to make predictions for new unseen data, right? And this is the crucial characteristics of a good machine learning model. It's a model which predicts the outputs for new unseen data with high quality. So actually, these numbers are our target, and we want to create a model which maximize these metrics. So for test sample. And let's try to understand how these errors, so two errors on the train set and on the test set, how these errors depend on model complexity. So here we have a very simple model and a very simple problem. So there is a very natural way to modify the complexity of our model. We can just change the degree of polynomial, and so to introduce some high degree polynomial and to increase the flexibility of our model. We can start with a simple degree 0 fit, so just a constant fit. And as I said, as we can see, it's R square for this model is equal to 0 or almost equal to 0 for the test set. Then we can use, say, this number of polynomials. We know that for this particular problem is this choice is the optimal one, just because the original function is 4-dimensional polynomial. And you see test R square and train R square are just good enough. Then we can try to increase the complexity further and say we can use a very high dimensional polynomial. Say we can use 10. And you see here we have a very good fit on the training data. So you can see that R square is just equal to 1. So from the first glance it should be a perfect fit, right? Just no errors on the training sample, on the training points. But if we check the results for the test set or just visualize the model, we can see that actually it's a really terrible model. It's too complex. It provides really high fluctuations here. We can try to visualize it. Say minus 100 to 100. Okay, as you can see, we have an outlier here. It's the range of our function is kind of from -1 to 1, and here we have -100. So it's a really huge outlier there. And also we have outliers somewhere, okay, somewhere inside. Well, these outliers are not as high. Okay, it seems that I refitted somewhere. I initialized the training sample again, so now we have a different image. So here it's not as dramatic as it was before with many peaks, but still we have this one really huge peak here. Well, and still R square is negative, is not say -1 million, but it's still a really huge negative number. And we can create a simple plot, so we can check different degrees, so from 1 to 20, and calculate errors. So here I plot MSE errors to compare this graph with some kind of a theoretical graph a little bit later. So here I fitted several models with different degree of our polynomial, and they just plot the errors. So this is the degree, and the red curve is related to train errors, and the green one to the test errors. So as we can see, if I increase the complexity of my model measured by degree, then the training error goes to 0 and R square goes to 1. As for the test error, we can see that it seems that there is kind of an optimal range of values here, and here the model is too simple, so it's kind of this one. Okay, I started from 1, not from 0. We can start from 0, and then here we can add a little bit different range. Yeah, so here we have the constant fit, right? So R square equal to 0. Then we increase the complexity and we benefit for all test sample and train sample. But then our model here, so it's actually it's the optimal point with degree equal to 4. Then if we increase the complexity further, it results in a dramatic increase in the test MSE. And this is kind of a typical behavior for many models, not for all, but for many models. And if you start with a very simple model, you have large test error. So again, test error is our target. We want to maximize the test error, and this is the most important thing for us. So here we have two simple model. Here is just a constant fit. Then we increase the complexity and observe that our test error is decreasing, and then at some point our model becomes too complex and the test error increases. Okay, so let's try to check this behavior for the same function, for the same model, but just using, so this is kind of a short summary. Again, here we have a really simple toy example, and here we generate our features. But imagine that in real life you have, say, 100 of data points and 200 of features. It's a common problem in, say, biological tasks, data science tasks. And here we can just reduce the degree. But well, if you have 200 of features and it's not clear can you drop some features or not. And a little bit later we will discuss that we can control the complexity of our model using regularization. But by now I want to provide you another example, again a simple toy exercise. Imagine that now we have more data points. So at the beginning we had 10 as far as I remember. Let's again this is the model with 10 points with these huge oscillations, and now we generate a new random training set. Now it's 5 times larger, so now we have 50 points, and we use exactly the same model, so not exactly the same, so it was 8. Yeah, here it was 8. Okay, we need to use the same number here. Yeah. So as we can see, now we have 50 points and polynomial degree, the same model, exactly the same as we had before. Degree equal to 8 and just linear regression. But now the fit is, I would say, almost ideal, right? We have some problems here, but the remaining part of the graph looks perfect. What does it mean? It means that there are two basic concepts. The first one is that the complexity of the underlying function. Here we have a really simple function, and actually we do not need degree equal to 8. It's enough to use degree equal to 4. And so the first concept is the complexity of the underlying unknown function. The second concept is that you can fit a complex model if you have a lot of data. If you have more data, you can fit a more complex model. And this is an example. And now we can build a similar plot as we had before. So again, here we modify degrees of polynomial, but now we fitted our models, these pipeline models with different degree, using this large data set with 50 points. And the results are shown in dotted curves, in dashed curves, sorry. And here, as we can see, so first, the overall MSE for our new model is better than we had before. So this increase in the training size results in better errors on the test set. Second, as we can see, we can use more complex models. So we can use degree 3, 4, 5, 6, I would say, maybe 7. But for 7, actually for 8, we have a similar error similar to the best error for the previous experiment. So it means that if we have more data, we have more opportunities to fit a good model. Second, the second observation is that if we have 50 points, it's harder to, even if we use 20 features, it's harder to get interpolation. So it's harder to move this error to 0. Actually, if we increase the number of polynomials to 50, this error will also be 0. But it's the most boring part of this exercise. So the key message here is that the complexity you can fit depends on the amount of the available training points. but the real complexity you may want to fit depends on the original underlying function, usually unknown. Okay. This is the next topic.